We live in a world of color. But what does it look like from the perspective of someone who's colorblind? Unlike what most people think, people who are colorblind can actually see many colors. It is very rare to only see shades of gray. People who have red-green color blindness see little or no distinction between the two colors. People who have blue-yellow color blindness see a more than slight distortion of color in their everyday lives. Here are some interesting statistics on color blindness. But what about the science of color blindness? What is it that makes people see color differently? Before we get into that, we must first recognize that each color in the visible spectrum has a set wavelength and energy level. As you can see, blue light has a very small wavelength and red light has a large wavelength. This concept also carries on to the energy levels of each color. Blue light has a very high energy, whereas red light has a relatively low energy level. In general, short wavelengths correspond to high energy, and long wavelengths correspond to lower energy. Now that we understand that, we can move on to the actual composition of your eye. In your eyes, there are rods and cones. Rods let you see shades of light, and cones help you to see colors. There are three types of cones in your eyes: L cones, M cones, and S cones. These letters stand for long, medium, and short, for the wavelengths of light they detect. A derivative of vitamin A, retinol is a substance found in your eye. In a test tube, a special reaction occurs when the light that hits it is 500 nanometers long. The energy of that specific wavelength of light causes the retinol to change from a cis configuration to a trans configuration. This natural occurrence is the key to understanding color vision. However, if you had nothing but retinol in your cones, you would only be able to see shades of gray, because this reaction would only occur at about 500 nanometers. This is when the opsin proteins come in. In your cones, opsin proteins envelop retinol, changing its chemical environment. Opsin proteins change the amount of energy required for the reaction to occur, allowing the detection of color. Now that we know how color vision works, we can understand how color blindness occurs. The most common case is red-green deficiency. This is so common because the genes for the red and green proteins are very close together on the X chromosome. Because they are so close, mutations can occur during crossing over in meiosis. Some scientists believe that translocation, or a point mutation, happens at that point, causing one of the said proteins, either the red or the green, to become similar to the other. Displayed here is a point mutation. Because of the mutation, now the L cone protein and the M cone protein look strikingly similar. Displayed here is a graph of the wavelengths detected by each of the three cones. As you can see, the L and M cones, or the red and green cones, are very close together, and because of the genetic mutation before, the L cone's range of detection slides even closer to the M cone, causing the person with these cones to have a red-green deficiency. There are also other ways in which one could be colorblind. A point mutation could code for a stop codon, thus creating a truncated protein. A frame shift could create a non-functional protein, or parts of a chromosome, and this is a chromosomal mutation, could be translocated. All this leads up to either faulty cones or no cones at all. Last but not least, color blindness is passed on with the X chromosome. Males are more likely to be colorblind because they only have a single X chromosome. Females have two X chromosomes, so if one of them coded for color blindness, the healthy chromosome would take over. In this video, we reviewed color vision and the reactions that occur. We have gone over color blindness and mutations. As a thanks for watching, here's a small test to see how well you would do in a colorblind world.